So let me quickly introduce. So Emilien Lavie is my PhD student. He's about to finish his PhD soon. So one of his work that he'll be presenting today will be about the COW protocol, the security of COW, and some of the modifications that he will introduce to you and how this would further enhance its resilience in the presence of loss. So Emilien, I hand it over to you to start the presentation.
Thank you, Charles, for the kind introduction. Hello, everyone, and thank you for tuning in. So yeah, I'm very pleased to share my results today with you about the security analysis of COW. I'll spend some time reviewing the current understanding of the security of COW and then highlight our proposed modifications and results. First, maybe for the non-expert audience, I want just to give a few words about what QKD is. So it's a cryptography protocol aiming at exchanging secure keys between Alice and Bob. And we expect that the key, it has to be secure against any adversary that could have tampered with the channel. A typical setup will basically have a sender that will encode states of light and send them over the channel. The channel usually will be a free space channel or optical fiber. And then the receiver will basically decode the incoming signals to try to extract information. But this part is actually just the beginning of the protocol. Actually, we need a few more steps in order to have a full QKD system. For instance, we need sifting. It's basically discarding part of the data that is not so relevant to create the key. And then we'll have parameter estimation. It's basically some processing on the data in order to estimate certain quantities of interest. For instance, we can have the bit error rate or the phase error rate that will be useful for the two next steps. The penultimate step is error correction. It's basically ensuring that Alice and Bob will share identical keys, and privacy amplification will ensure that that key is secret. That means that there is no correlation with any third party. After doing all of this, then we have a secret key that can be used for any application. And usually we think of symmetric encryption. Also here, I didn't write, but we still need some initial secret key to kickstart the process. So we can think of QKD more as a key expansion protocol rather than just creating secret key from nothing. So today I will only focus on the first part and especially on one particular design called the coherent one-way QKD protocol. It has been proposed many years ago, and this is how it goes. We have Alice, the sender, who is using a coherent laser with an intensity modulator, and she will basically be creating sequences of empty and non-empty pulses. So a sequence of empty, non-empty, or vice versa will determine the bit value. And once in a while, if there are two subsequent pulses that are non-empty, it will create a decoy state that is used to test the channel. On the receiver side, we have one unbalanced beam splitter that will split the light between one direct line and one monitoring line. The direct line is just a simple detector that will measure the time of arrival and decode whether we have bit 0 or bit 1. And the monitoring line is basically a Marsender interferometer that will just interfere two subsequent pulses to check the coherence between them. If the coherence between the two pulses is broken, basically the channel is not secure. So this is what we want to detect. And to quantify this quantity, we use basically a sort of ratio between the detections of these two detectors, something usually called the visibility. So now why is this scheme interesting? Well, it's because it's actually simpler than other designs. Simpler because the sender only has an intensity modulator and there is no phase modulation involved. And also the receiver only has fully passive optical components and also no phase modulation. We have a few reported experiments using this scheme, and even commercial devices are being sold using this protocol. So we see that it works in practice. It has been tested. So why am I talking about it today? Well, it's because the security is not completely understood, and it's not clear if it's completely secure, actually. That is because basically we like to analyze the security of protocols when we have elementary rounds like this that are repeated many times independently. This is an IID structure. But here, just by design, we can have also some correlation between different rounds, and this makes the analysis more challenging. So usually to find results despite this structure, we have to make additional assumptions. So I will review the current understanding of the security. So we have a few early works that were published a long time ago. And first, when I'm talking about the security, actually, I mean the secure key rate. This is the rate at which the system can operate and the rate that can be proven secure. Unfortunately, this rate is usually difficult to compute. So instead, we can analyze upper or lower bounds. When you have upper bounds, that means that the system cannot operate at a faster rate because there is already a known attack that might break the protocol at a specific rate. And conversely, having lower bounds gives a security guarantee because we know that at that rate, it is impossible to to break the protocol. Ideally, we like having lower and upper bounds that match so that we know that the rate is optimal. So here on the left, we have a paper that studied some upper bounds on the protocol. So for instance, we have this top one, which is the beam splitting attack bound. Beam splitting attack is a very simple attack, maybe the simplest one can think of, because it's simply giving all the losses on the channel to the adversary and checking how well it can guess the secret. And then the authors, they also try to analyze more sophisticated attacks, and they found out that actually they also have the same scaling, which is linear with the channel distance. So at that point of time, maybe we can think that the security effectively scales linearly with the channel distance, but we might be overlooking a more powerful attack. So on the right, we have this paper instead that tried to analyze lower bounds, but to do so, because of the non-IID structure being difficult to analyze, they had to do some modifications to analyze the scheme. So here, instead, they proposed to use an active receiver with an active switch to choose between the data line and the monitoring line. And even in the monitoring line, they don't have a Mach-Zehnder interferometer, but instead they also have a switch that will send the first pulse in the first arm and the second pulse in the second arm. This is essentially to avoid an extra 3 dB loss that we usually have when using a Mach-Zehnder interferometer. They also have photon number resolving detectors here, and they also use a slightly different pairing of the pulses. So it's significantly different from the original design, and they could prove a bound that is only scaling quadratically with the total loss. More recently, we can find this work to which I also contributed. And basically, we tried to remove the photon number resolving detector assumption, and we analyzed the security with just regular threshold detectors. We found out that we can only guarantee a security bound that scales terribly, much lower than quadratic if we use the original encoding, so the test states alpha alpha. But instead, if we use a lower intensity, we found that we can push it to actually a better bound. Okay, and one more paper. So this one actually analyzed upper bounds, so attacks on the actual protocol. And the authors found that for a special type of attack called sequential attacks, it's basically a combination of minimum error discrimination and unambiguous state discrimination. They found that it's possible to break the security of COW at a rate that scales quadratically with the channel loss. So that means that the original design will just never beat this quadratic bound. But still, it's an upper bound, so we don't know if the actual security is quadratic or anywhere close to that bound, or if it's much worse. After releasing this work, actually one of the authors, Marcos Curti, proposed some countermeasures to render the attack a bit less effective. And I selected one countermeasure that I will analyze here. It's using an additional test state composed of only vacuum pulses. And by doing so, he found that the bound becomes actually better than quadratic now. But again, this is only an upper bound, and we don't know if this is the effective security, or maybe it's still quadratic, or maybe still worse than quadratic. So this is what we try also to solve today. So we are trying to analyze lower bounds. And again, because of the non-IID structure, it's a bit difficult to address. So we considered modifications to enforce an IID structure. And we try to have very minimal modifications. So I will mention them now. So a first modification we use is to add an extra vacuum pulse at the end of the trains. And this one is really to empty the interferometer here, because the middle pulse, when it enters the interferometer, half of it will be directly detected and half of it will be delayed till the next time bin. And the next time bin would be the early pulse of the next round if we don't have this extra pulse. And this we don't like because it will basically interfere different rounds together and mess up the analysis. So instead, we prefer to have one extra pulse that will completely empty the interferometer. We also allow a lower intensity in the test state, just like before, because we realized that it might give better performances. And another major modification is this beam splitter here. We consider a 50-50 balanced beam splitter for the passive basis choice. And this is currently just a limitation of the proof technique. So maybe in the future, we'll be able to go around it and allow any imbalance in the beam splitter. And all the rest is just the same. We have the Masander interferometer and we have the threshold detectors. So now we'll move on to the security analysis, and it's
sorry, is it possible to make questions on the way, or is it better to leave them for the end?
Or if you think that this is a good time, then just go ahead. I don't mind.
Then it's a curiosity, because you made these modifications, as you explained. Maybe there are some technical reasons for your security proof, but in principle, we know that typically the scaling of a protocol is not good if it is vulnerable or is not robust against an ambiguous state discrimination. And if you select just 3 states that are linearly independent, as you're doing here, and you don't plan to check coherence between them, then it's clear that there is always an ambiguous state discrimination attack that will work. So I was wondering why do you think this is the right way to go?
That's a good question. Actually, correct. There is always a USD attack possible, but there are also some conditions, and the rate at which the attack will succeed is not 1, basically. So it will never be perfect. So there is some basically space for exchanging a secret key.
Yeah, that's true. But I mean, we know that if it is not robust against an ambiguous state discrimination attack, one cannot expect a really good scaling. So you know already a priori that there will be clear limits where you can go.
Yeah, definitely. But at least we want to know what it is to see if it's just terrible or if we can reach a quadratic scaling.
Okay, thank you.
And also, just to give you maybe more insights, oops, I need to annotate. Okay, here. These states, actually, the original intensity was alpha alpha. And actually, we found out that it's better to reduce the intensity of this guy. And it's basically because we want this one to be approximately equal to 0 alpha plus alpha 0, just the cat state of the two. And basically, if you try to maximize the overlap between these states, you will find that it's better to have a lower intensity. So indeed, this is to reduce the power of USD attacks just by making them less distinguishable. Okay, so I'll move on to the security analysis. The first ingredient is squashing. So a few words about squashing. The issue is that the receiver will operate on the incoming state from the signal, and this could be of arbitrary dimension. But unfortunately, the security analysis is usually formulated in terms of finite dimension systems, just because it's simpler. So it's not completely clear if we can directly apply the security analysis formulated for finite dimension systems directly on the statistics that we observe for any state, any incoming state. So in this paper by GLLP, like they proposed a popular approach called squashing. And they basically say that if we have a situation where we have a virtual operation called a squash map that will project the input state onto a more relevant subspace, so typically a single photon subspace. And if we can show that the two situations are equivalent, then it's okay to directly apply the security analysis on the actual situation. This paper, they show that it's possible to find a squash map. They gave a method based on semi-definite programming techniques, but it's not always very good. Sometimes we need to pay a huge penalty in terms of adding white noise to find a squash map. And for certain protocols, like the 6-stage protocol, it's not clear if there is, we know that it's not easy to do. And for our case, we don't really know. We know that in this paper I mentioned before here for the receiver, they found a squash map to describe the receiver. But for our case, using an interferometer, here it's not clear if we can get one actually. And to be honest, we didn't even try to find one, but instead we relied on this result that we think might have been overlooked by the community, because it gave us a very nice result with limited efforts. And it's basically saying that we are not obliged to have exact statistics on the single photon protocol, but if we just have reasonably good upper and lower bounds, then it's enough. And if we allow this relaxation, it's actually easy to get bounds. Roughly speaking, we can just take the single click rate and just do plus minus the double click rate, and this will give the bounds on the single photon statistics. So after we do this step, we have the bounds on the single photon statistics, and we can directly apply a security proof. So we choose to use numerical methods because they usually give better key rates for a large variety of protocols. And here we have these two papers that are applicable in our case. The first one is minimizing the quantum divergence. It's basically rephrasing the von Neumann entropy that appears in the De Vita-Quinter key rate bound. It's nonlinear, so it's pretty slow in practice. So instead, we use the second one, which is based on maximizing the phase error rate. The phase error rate is appearing in the low prescale key rate, which is another bound on the De Vita-Quinter bound. In practice, we found that those two methods are giving similar results, but since the second one is much faster, this is the one that we used in our plots. So now this is finally the results slide. So I'll take some time to describe what we have here. So we have some reference upper bounds. So the top one is the secret key capacity. This is the fundamental bound on the key rate for point-to-point communication. It's scaling linearly with the channel loss. Below, we have the sequential attack bound. So we know that the COW protocol will never be able to beat this bound. And then we have our results. So the dashed line is the performance that we get last time when analyzing the security with the active switch and the numerical method based on NPA hierarchy. And the dotted line is the performance that we get in our with this squashing method. It's very surprising, but actually they give similar results. It's just slightly lower in the low loss regime, and we think that it's because of the penalty when using the bound with the double click rate. In the high loss regime, the double click rate is very low, so the two bounds become essentially the same. Now the red one is when we have the alpha-alpha encoding, so the same encoding as originally. And the green one is when we have alpha over 2. So when we use a lower intensity, again, we find that we can indeed certify a bound that is much better. And the purple dotted line is the bound that we obtain when analyzing the countermeasure proposed by Marco Scotti. So when we use an extra test state with vacuum, we can actually also push the security much further. The solid orange line is just for comparison, is the coherent states BB84, phase encoding BB84. So it's just to show that it's basically the same type of performance. Okay, I also have a plot in the noisy case with 1% error rate and 98% visibility. And it's basically the same, just a bit lower because of the noise, of course. So just to summarize, so the results that we find with the squashing method are surprisingly similar to what we found before with the NPA numerical method and active switch, even though there are substantial differences between the two security proofs. We've also found that the countermeasure using additional vacuum states is very effective, but R-bound is still not breaking the quadratic scaling. So maybe it's not as good as beating the quadratic scaling, or maybe just our analysis cannot show it. And one additional point I would like to mention is that the bounds that we find are essentially tight because we're using convex optimization techniques, and usually they come with a certificate in terms of duality gap. So it's just saying that an upper bound is basically very close to the lower bound that we find. I have this summary plot, which is the same as before, but simplified to clarify our claim. So we propose a method with a modified version of COW to have bounds. We are not using the intersignal phase information. So that means that possibly the original design, which is using this information, might perform better, but we don't know yet. But anyways, this original protocol will never be able to beat the quadratic bound. But what we find is that even if we ignore this phase information, we are still able actually to reach pretty close to that bound. So maybe it's enough in practice to just consider one of these two modifications. And now I guess you're just left with choosing your team. Either you consider that it's easier to implement an additional test state, or maybe it's easier to modulate the intensity of the existing test state. We have a manuscript on its way. It's not quite ready yet, but we hope to release it in the coming weeks. And I guess that the next natural step will be to check the security with real life data instead of just some ideal simulations. So that's all for me, and I'm looking forward to hearing your thoughts about this study. Thank you.
Hello. Emil, this is Marcos again. I have another question. So first, thank you for the very nice presentation. It has been very nice and very clear. Your results confirm more or less what I mentioned before. Since you know that you have linearly independent states, then you know that the performance cannot be better probably than quadratic. But I just have a curiosity, because now that we know that there is this scaling and you see that you can actually reach it, have you compared it with the BB84 with laser sources and without decoy states? Because we know that we have the same scaling as well there. So that means if we just use
the coherent states BB84.
Yeah, exactly, without decoy state, no decoy state.
Yeah, correct.
And we have the same scaling, but I was wondering if the key rate is essentially the same or which one is slightly higher than other.
Yes, actually I did it, and here on this plot, this is the solid orange line, and it is basically the same performance.
Okay, sorry, I missed that. Sorry. Okay,
yeah,
I see it.
No worries.
Thank you. That's what I expected. Okay, thank you.
Hello, Emilien, this is Romain. So thanks for the nice talk. You have a generic question, maybe also from Marcos, but so what would be the solutions or the path for going beyond the quadratic scaling, so that you somehow hint, but does it give clear insight of what would be needed or possible? I mean, keeping essentially also the hardware.
Yeah, indeed, here we have this quadratic scaling, and if we want to go beyond, the very popular technique is to use decoy states. Yes. That is because basically the states here, the coherent states, they have a large overlap, and well, they are easy to distinguish actually, or easier to distinguish than having qubit states, for instance, like the original BB84. So one way to go around it is to use decoy states. In order to do it, we need an additional, like additional states. Actually, we need to change the intensity to have the actual state and lower intensities. So basically, we would need more states to send. And we also need a phase modulator. So this is on the source side. And for the detector side, it's also possible to use something similar to decoy states, but this will probably be irrelevant here because we need to modulate the efficiency of each single detector. I don't know if this answered the question, but yeah,
why do you need phase as well?
We need a phase because the decoy states method is based on phase randomized coherent states. So we can either choose to just turn on and off the laser, but it's usually slow. So instead, we prefer using darkly phase modulators to randomize the phase of each signal.
Okay, so here the fact that it's not phase randomized is taken into account in the proof. You don't assume it. You take it.
Yes.
Okay. Okay, thank you. Thank you, Emilien.
Thank you for a very interesting talk. Maybe I missed something, but here you have these 3 pulses with your tail vacuum. And in the result, I didn't see that. I thought you were back to the standard ideas. Is that correct, or is it a misunderstanding?
Yeah,
yes, exactly.
Yeah, you're correct. Indeed, here I'm still considering 3 pulse. It was just to have like a lighter figure, but you're correct. You just happen vacuum everywhere.
Okay, so your proof relies on the fact that for each of these, you have 1 vacuum before or after of all these pulses. Yeah, okay, clear.
Yes, correct.
Yeah, that's what and then the next question is, why don't you mix these 2? For example, you could have, you could add a vacuum state also to the last one, the alpha/2 and alpha/2.
Yes, good question. Actually, I also checked this, and this will give basically the same performance as the green line. So
okay, so the fact that you prevent this USD, okay, the fact that you prevent then the USD measurement does not help anymore if you have this alpha/2, alpha/2.
Yeah, indeed. So. Okay. My personal understanding of this is that, as I mentioned before, having this alpha/2 is making the USD more difficult because then this state is not so distinguishable from the cat state, the superposition of these 2. And actually, it's slightly similar when we use this pair of test states. So actually, if you think about it, having this alpha/alpha and vacuum/vacuum, it's a bit like having total intensity 2 alpha over 4 places. So on average, you have alpha/2 everywhere. So my understanding of this is that basically this pair of states, they basically simulate this alpha/2.
Okay, very interesting idea. Okay, thank you.
Thank you very much for this nice presentation. Well, it's a kind of how should I say that, funny, maybe it's not really funny, but of course COW was invented to get rid of this quadratic bound, no, what we already had with the BB84 at the time without decoy state, and we wanted to improve it, of course. And now it turns out it's the same, and so we can keep the old BB84 system in principle. And now, well, of course, with this additional states, a little bit what you introduce, you can at least save this quadratic bound, but then experimentally, I think it's the same complexity like a decoy state, free state BB84, like we do it now. So it's kind of it's a nice improvement for the COW, but experimentally doesn't make a lot of sense to work on COW anymore, because it's like this anyway. It's as complicated as another system, and which is much more performant. But yeah, it's a nice result anyway. Thanks.
Yeah, I'm not sure actually, because I'm not an experimentalist, but since everything is using passive optics, it might be possible to just have a very fast repeating rate and maybe gain something thanks to that. Like, of course, we have a not so good scaling, but maybe if we can like multiplex or operate very fast the system, maybe it will still be useful to have a QKD system based on this protocol.
Yeah, you know, in the now new protocol, you also have a passive system at Bob, and on Alice side, you need a rapid intensity modulator. And what changes is that you have this pulsed laser instead of a CW laser. And of course, the CW laser is a bit simpler, but it's not the pulse laser which limits us in the rate. So we can pulse it at a high rate, and we are still losing this phase correlation between adjacent pulses, even at rates up to almost 5 gigahertz or something. So we have our limitations. So it's not, well, maybe one day you want to go to a completely integrated on a chip. Maybe the CW laser may have an advantage, but the system as it is now, it's really experimentally, it's almost from the same complexity. So that's why we prefer now this free state decoy state setup.
Hello, Emilien. I also have a curiosity, very nice talk. In the previous slide to this one, where you show the rates compared, this one, where you have also the coherent state BB84. I had a curiosity. So if you see your protocol, no, with this beta equal to alpha over 2.
Okay.
No, it's kind of like 3-state BB84, no, more or less. Like if I eliminate like one of the BB84 states, no, like you should have alpha over square root of 2, I think, and then in the other one with the different phase. And here you take out one of these 2 states, and you change a little bit the intensity, and then you get a better rate. Do you have an intuition why it's that?
Okay, actually, it might. I think I've never said that we completely beat this protocol. They are just like similar in terms of performance, especially the plot that I draw here. The Q rate formula I use is the low prescale Q rate. We have an analytical formula, and actually there are also numerical analysis of this protocol that gives better Q rate. It's just that I didn't have time actually to plot the full curve, so I plot this one faster. But they are probably around the same.
Okay. Yeah, makes sense. Thanks.
Yeah, Emilien, if no more question, then maybe I can add one small remark, to wrap up the entire presentation, which was very nice, by the way. So I guess one of the motivations for us in getting Emilien to do this work is that after the very nice work done by Marcus in providing the upper bounds on the COW protocol, we really wanted to ascertain whether this is the loose upper bound, or one could further introduce new modifications that would further enhance the performance of COW. So the only way to check this, right, is to derive a tight lower bound that will eventually, either match the one given by Marcus, or with a certain modification go beyond what has been done with the original COW protocol. And I guess with this, the findings of Emilien, we can more or less conclude that the COW protocol, for what it's worth today, right, is pretty much limited to the quadratic bound. And yeah, I mean, and to the comment of Hugo, I believe it's not like the death of COW, right? It's simply going to might find some use cases in other deployment settings. So yeah, you never know. And the modification that we need to get to this quadratic bound is not dramatic either, right? It's just to change additional level of intensity. Okay. If not, then I thank everyone for taking time, especially from Europe, our friends. Otherwise, yeah, stay safe, and we would see you soon. Hopefully, right? Hopefully for QCrypt. I hope. Yeah.